Hello everyone! It's a pleasure to be here today. My name is Eduily Freire. I am a PhD student from Federal University of Sergipe, and today I'm going to talk about my work with cadmium silicates. This presentation is entitled Computational Modeling of Cadmium Silicates Doped with Rare Earth and Transition Metal Ions. Let's go! So, first, materials that have the characteristic of persistent luminescence have been widely studied, mainly because of many applications possibilities, as emerging signs, luminoceramics, and as we can see in these figures. It can also be applied in bioimaging, as is the case of this work with gadolinium phosphorate. However, in cadmium silicate matrices doped with different rare earths, similar results are reported. That is, luminescence in different colors use only the matrix CDSCO3 for this purpose. Here you can see in this paper cadmium silicate doped with dysprosium, gadolinium, terbium, samarium, and praseodymium. And we identified the different colors of luminescence depending only on the doping ion. We can see that these colors can be from violet to red, even close to white when doped with dysprosium. Okay, and now another important fact to be said is that even in pure materials, without any doping, it has long-lasting intrinsic luminescence, two regions of the visible spectrum. In the first region, we have a luminescence in red, and in the second region, in blue, as demonstrated by Freire. Okay, in the CDSCO3 matrix, single doped can be made. That is, use only one dopant and obtain emissions colors in different regions of the visible spectrum. But we also find many works that doped double and obtain luminescence in other regions of the visible spectrum. This fact is of great interest because it makes possible to choose the doping ion according to the desired luminescence colors. Okay, now we will present the matrices studied in this work. Okay, this is the CDSCO3 matrix. In purple, we have cadmium ions, and in blue, we have silicon ions, and in red, we have oxygen ions. This matrix has 3 symmetrically non-equivalent cadmium and silicon ions, and 9 symmetrically non-equivalent oxygen ions. This fact will be important when we evaluate these defects in the matrix. Okay, now we have the CD2SeO4 matrix, and it has only one symmetrically non equivalent sites for cadmium, silicon, and oxygen ions. Okay? Now, here we have the CD3SeO5 matrix, and in this matrix we have two symmetrically non-equivalent cadmium and two oxygen sites, and only one symmetrically non-equivalent silicon sites. All matrices are in the ICSD database, okay? Now that we have introduced in cadmium silicate matrix, let's talk about the extrinsic defects in these matrices. Okay, first, we have to evaluate what are the solution equations for charge compensation. Considering that our doping ions have a 3+ valence, okay? We consider 6 different possibilities for doping. The first is to place 2 doping ions at the sites of 2 cadmium ions, compensating the charge with a cadmium vacancy. The second way is to place 2 doping and at the cadmium sites with charge compensation by an interstitial oxygen. The third way is to place 4 doping ions at the cadmium sites and to compensate the charge with an oxygen vacancy. The fourth way is to place 4 doping ions at the silicon sites and compensate the charge with an interstitial silicon ion. The fifth way is to place 2 doping ions at the silicon sites and to compensate the charge with an oxygen vacancy. The sixth way is to place 2 doping ions on the silicon sites and compensate the charge with an interstitial cadmium ions. So now we will identify where the interstitial sites be inserted. For that, we found regions of our solid where there is at less 1.5 angstroms away to the nearest ion. We found 3 symmetrically non-equivalent positions for the interstitial ions in the CDSCO3 matrix and 2 symmetrically non-equivalent positions for the interstitial ions for the CD2SeO4 matrix, and we found 3 symmetrically non-equivalent positions for the CD3SeO5 matrix. For the inclusion of defects in the matrices, we chose the multi-little method, which divides the material into 2 concentric spherical regions where the center is the defect, and we optimized our structure based on the defect. Our calculations we performed using the GUP program, which is a classical program calculations, and were performed in static and periodic manner. Okay, We use two forms of identifications for defects. The first form is what we call unbounded defects. In this form, one defect ion does not interact with the other. That is, they are far enough away to not feel the effect of the other defect. Another characteristic is that they are always necessarily in different unit cells, okay? And we have the bond defects, the ions in bond defects that form the defect can interacting. They are usually in the same unit cell or in neighbors unit cells. However, the maximum distance for a defect, if called bond, is maximum of 12 angstroms, precisely because the fact that our short-range potentials have a maximum range of 12 angstroms. Okay, going now to results of extrinsic defects. Here we have the graphic of the CDSCO3 matrix at 0 Kelvin. Here, each of these colors represent a type of extrinsic defects. This graphic is a graphic of normalized solution energy by defects for each of the doping ions, okay? And then we can observe that the most energetically favorable extrinsic defects is the defect with two doping ions at the cadmium sites plus a cadmium vacancy for all hard earth ions, and two doping ions at the silicon sites with charge compensation by an oxygen vacancy for the transitions metals. Okay, next graph. In this graph show the solution energy for extrinsic defects in the CDSCO3 matrix at 300 Kelvin for all dopants with valence 3+. We observed that it followed the same things for hard earth dopants and for transitions metals dopants. Okay, now we have the graph for the CD2SCO4 matrix at 0 Kelvin. In this graphic, we see that doping with hard earth follow the same way seen for the CDSCO3 matrix. However, there is a big difference for the transitions metals because in this matrix we observe that they also enter the cadmium sites plus a cadmium vacancy, with it has not expected for the CDSCO3 matrix. We also observed a smaller number of points in this graphic. This is due to the existence of only one symmetrically non-equivalent sites for the matrix for cadmium, silicon, and oxygen ions. Okay, again, here we have the graph of the CD2SeO4 matrix now at 300 Kelvin. And we observe the same things when compared with the CD2SeO4 at 0 Kelvin. We can see that just like in the 0 Kelvin matrix for Her8 and transitions metals. Now, for the CD3SeO5 matrix, we have the graphic for 0 Kelvin, and where we identified that is less energetically defect remains the same of the CD2SeO4 matrix for Her8 and ions, and else for transitions metals. Now, for the graph of the CD3SeO5 matrix at 300, we continue with the same things for the same matrix at 0 Kelvin, and else for the CD2SeO5 matrix, but for the lowest energy and for second lowest energy. With that, we included the unbounded defects for the three matrices studied at the two temperatures. Okay, now we will see the bond defects, and for that we choose the first and the second less energy form for the extrinsic defects, okay? These calculations were only done for the CDSCO3 matrix, okay? The last energetic defect we have for Her8 is with two doping ions at the cadmium 2 sites plus a cadmium 1 vacance. As for transitions metals, the less energetic defect is with the doping ions at the silicon 3 sites plus an oxygen vacance 5. This for both temperatures. For the second smiled energy, in Her8, it is with doping ions at cadmium sites 2 plus an interstitial oxygen 1. And for the transitions metals, we have the doping ions at the silicon 3 sites plus an interstitial cadmium 2. Okay? Now, looking at the graph of the bond defects in the CDSCO3 matrix at 0 Kelvin, in green we have the date for the defect of the last energy, where M is the doping ion, okay? And for transitions metals, we have the lowest energy given by this equation here. Okay, we also made the graph for CDSCO3 matrix at 300 Kelvin. We see in this graph that there is the same things when compared to the graph at 0 Kelvin. We observe that there is a lower energy configuration always in focus. In Her8 and else in transitions metals. Okay, looking now at this table, we can see the relationships between the energy, the distance between the ions, and the diedral angles. This table refers to hard earth doping ions, and we can observe an alignment trend between the ion involved in this defect, with the lowest energy being at the position where the angles is 177 degrees between the defects. There is also a performance distance, which is approximately 7 angstroms between the most distant defects. Looking now at the ions that form the defect, we can see in the imaging the angle formed, where is the vacance is centered. Okay. For transitions metals, we have the same trends as before, changing the ions involved in this configuration. The less energetic defect is at the diedral angles of approximately 127 degrees, and the distance continues at approximately 7 angstroms. In the picture, we can see the configuration between the ions involved for the formation of the defects. This point in yellow. Okay. Well, to finish the results, I will now present the comparison between the bond and unbound defects in the CdSeO3 matrix at 0 Kelvin. Here, for the bond defects, we have a much lower energy than in the unbound defects. And more, all the bond defects for hard earth have less energy than were the lowest energy for unbound defects. Okay? Well, now for the conclusions, we have first, we have that the less energetic defects are for hard earth 2 doping ions at the CD2 sites plus an cadmium vacance, and for transitions metals 2 doping ions at the silicon 3 plus an oxygen 5 vacance. However, we know that the undoped CdCO3 matrix has 2 luminescent centers, in blue caused by cadmium vacance and in red due to defects in the silicon lattices. In this paper, we found that the less energetic intrinsic defect is the pseudo-Schottky of CDO as formed by cadmium and oxygen 5 vacance. Its very interesting fact is that intrinsic defects and extrinsic defects generate the same vacance in the matrices. This fact contributes to the fact that intrinsic and extrinsic defects have a common origin, which is the pseudo-Schottky of CDO defects. Finally, I would like to thank CAPES, CNPq, Senapad, or Group LPCM, and Federal University of Sergipe. Thank you for your attention. Bye!